So, we can get chain reactions and use them to destroy cities, but that's not very useful as a power source. Is there some way that we can tame this runaway process of chain reaction? Well, what do we need? Well, we need a chain reaction. Relying on the natural radioactivity is not going to do it. So which means we need enough of uranium-235, not the more common uranium-238. And we need to set it up so you can get the chain reaction, which means not too much absorbing materials, a critical mass. And actually it turns out that neutrons have a much better chance of causing a chain reaction when they're moving slowly, so we use moderators to slow the neutrons down. But we also need control. We don't want to just let it run away, we want to keep the energy generation at a rate that we can handle. Then we need to take all the heat and use it to generate electricity with some sort of heat engine. And we need some sort of cooling to stop the whole thing just getting too hot and melting down. So first of all, we need the fuel. So first of all, mine the uranium. It turns out that Australia has the world's largest known uranium deposits, about 1/3 of all the world's known uranium deposits. Now there's uranium everywhere at very low levels. Almost every rock contains a little bit of uranium, but it's uneconomic to mine unless it's being concentrated by geological processes. Australia has a lot of the world's uranium, but it's actually only the 4th largest producer. Other countries produce a much larger fraction. The Olympic Dam in outback South Australia is the world's biggest known uranium deposits. They're actually mined as a byproduct of copper. The reason is the Olympic Dam is only 0.04% of the ore. So you need to mine 2,500 tons of ore to get 1 ton of uranium, which would be uneconomic if it weren't for the fact that a lot of the rest of the stuff is copper, which is also valuable. So while they're mining the copper, they can get the uranium out as well. But because it's a very large volume of rock, even though it's only 0.04%, that's still the world's biggest known uranium deposits. Now this is processed into a substance called yellow cake, which is uranium oxide. It needs about 200 tons of uranium oxide to power a decent-sized nuclear reactor, 1,000 megawatts of electricity, for a year. That sounds like a lot, 200 tons of uranium, but the similar coal plant would need 9,000 tons of coal per day, not 200 tons per year. So that's telling you the incredible energy density of this uranium. But the uranium just by itself is not very useful because only 0.7% of it is uranium-235, because the rest has decayed over the last 4.6 billion years. The rest is uranium-238, which is not useful for chain reactions because a neutron passing by it doesn't cause it to fission. So for most reactors you need to increase it. If you try to build an atom bomb, you increase it very dramatically. It has to be enriched up to like 70, 80 and 90% uranium-235. But for nuclear reactors you can get away with 3, 4, 5%. And in fact there are nuclear reactors, the CANDU style, pioneered by Canada, which can actually use natural uranium. But normally most reactors use about 4% enriched. And this is tricky because uranium-235 is an isotope of uranium, as is uranium-238, which means they have the same number of electrons and the same energy shells, so chemically they're identical. There is no chemical process that can split one isotope from another of the same element, because any chemical reaction that will apply to one will also apply to the other. So how is it done? At the moment it's mostly done by using whole arrays of centrifuges. This is a room full of centrifuges in the US. Each of these things is like 3 meters tall, so a person is much smaller than them. These are incredibly sophisticated devices that spin at incredible speeds, and you convert the uranium into a gas, uranium hexafluoride, and as it's spun, the intense centrifugal force moves the uranium-238, which is 1% heavier, more to the outside, whereas the lighter uranium-235 is more near the middle, and then you pump out the gas in the middle, and then feed it into the next centrifuge, where this is done again. Now the amount of concentration is very small at any given centrifuge, but by going through one after another, after another, after another, after another, you can concentrate the uranium-235 until at the end, after going through all these huge numbers of centrifuges, you can get it up to a larger percentage, which is what you need for a nuclear reactor. Now this is the hardest part of building a nuclear reactor, and it's also the hardest part of building an atomic bomb, and thank goodness for this. If we lived 2 billion years in the future and natural uranium had much larger amount, it would be much easier to build atomic bombs. So a lot of the work in trying to stop countries developing atomic bombs is going to stopping them from getting centrifuges. The famous case is the Stuxnet computer virus. A whole bunch of centrifuges have been sold by a German company to Iran, which they were using it to refine uranium to build bombs. But a rather mysterious computer virus was injected into the control software for these things, a Stuxnet, which causes centrifuges to spin too fast and destroy themselves. Probably some combination of American or Israeli espionage to destroy the Iranian nuclear weapons program. But once you've done this, hopefully you can enrich it up to a few percent, which is what you need for a nuclear reactor, and not all the way up to 70 or 80 or 90% for an atom bomb. The uranium is then turned back into a solid and typically baked into ceramic pellets of uranium oxide encased in metal tubes. This is to make it fairly safe, so when it gets radioactive it's still reasonably easy to handle and doesn't turn into some sort of gas or dust that could spread around. And now we need about 27 tons of this enriched ceramic pellets for our 1000 megawatt electricity reactor. So as you can see, only a very small fraction of the thousands of tons started off have ended up in the actual reactor.